also you have learned in energy balance and also thermodynamics. Okay, so chapter 3 is the actual content of this course. Okay. Okay, chapter 3, volumetric properties of pure fluids. Okay, so this is the content, okay, for chapter 3. Okay, first you have the introduction to volumetric properties. Okay, and then I'm going to explain about the PVT behavior of pure substances, volumetric properties from equations of state. So you're going to learn these equations: ideal gas equation, virial equation, generic cubic equation. And then volumetric properties from generalized correlation. So we will be doing for gases and also for liquid. And also volumetric properties from thermodynamic tables and diagrams. So basically chapter 3, you are going to learn about the PVT. Okay, so P pressure, V volume, and the T is the temperature. Okay, so the topic outcomes are listed here. It is expected that students are able to first determine the state or the phase of a given fluid at given conditions, calculate the volumetric properties using the equations of state and generalized correlations for a given system, identify the applicability and limitation of every equation of state, and determine the volumetric properties from thermodynamic tables and diagrams. Okay, let's go to the first part, which is the introduction. Okay, so this diagram here, if you have your textbook, this diagram is the same diagram as in page 65, yeah? Okay, page 65 of your textbook. So here you have the pressure. Okay, pressure on the y-axis and then the temperature on the x-axis. Okay, so when you vary the pressure and when you vary the temperature, you can actually see the different behavior of the substance. Yeah, so it can change the phase or the state. Okay, so okay, this next slide here, this is actually the same figure as the previous slide. It just that it shows more explanation here. Okay, so here you have the different region. Okay, and again remember, this is for pure substance. What is the meaning of pure substance? Meaning that you only have one type of substance. Okay, if it's methanol, then it's methanol only. Okay, if it's water, then it's water only. It is not mixed. Okay, so in this case you have the first you need to identify the three different regions. Yeah, so you have the solid region here, and then the liquid region, and then here you have the vapor region. Okay, and these three regions, they are separated by what we call these three curves here. Okay, so for example, the vapor region and the solid region they are separated by this sublimation curve. Okay, so this line from line 1 to 2 is the sublimation curve. Okay, so it separates the vapor and the solid region. And then line 2 to 3 is called the fusion curve. Okay, so the fusion curve separates between the solid region and the liquid region. And then you have line 2 to C. So this is the vaporization curve. So vaporization curve separates between the liquid region and the gas region. Okay. And then we also have the fluid region here. So this point C, if you look at here, this is point C, and the pressure at point C is the PC, which is the critical pressure, okay? And then the temperature at point C is the TC, the critical temperature. So if you have when the temperature and the pressure is above the critical pressure or the critical temperature, then the region here becomes the fluid region, okay? Okay, here. All right. So when you have, when the temperature is higher than the critical temperature, we call this as supercritical condition, okay? And then point C here is called the critical point. That's why we use the symbol C to indicate that that is the critical point, yeah? Okay, and then oh yeah. Okay, and then you have another point here, this green point in the middle here, where the three lines meet. So this point is called the triple point, okay? And the triple point is where you can find all three phases coexist, meaning that on the triple point, you will have the solid phase, the liquid phase, and the vapor phase all coexist together, okay? And then when you have the lines, okay, for example, here the sublimation curve, when you have the lines, the point on the line is where the substance exists in two phases. So on the sublimation curve, on the sublimation line, the solid phase and the vapor phase, they coexist together. Okay. Similarly, on the vaporization curve or the vaporization line, the vapor phase and the liquid phase coexist together. Okay. And on the fusion line, the liquid phase and the solid phase coexist, meaning you can find the liquid and also you can find the solid only on the line, okay? The rest of the area where here it exists as the single phase, okay? So you have the solid, the liquid, or the vapor. All right. Now, okay, so sometimes we mention state and sometimes we mention phase. So these two terms, they are very similar but slightly different, okay? So a state is defined as a form that matter can take. So you can say, okay, so this methanol is in liquid state, okay, meaning it's in liquid form, okay? We can also refer to as the phase, which is a region of space where all physical and chemical properties are uniform. So when we say state, normally we refer to a single state. Okay, so let's say we say this methanol is in gas form, it's in liquid form. When we say phase, it's basically it means it refers to the region. Okay, so normally we refer to this graph. So which region it refers to? So the region here is the phase. Okay. All right. So related to this diagram, I think you have learned about this before, the degree of freedom. So F, this equation here is for the degree of freedom, which is shown by F. Okay, so DOF is the degree of freedom. So the degree of freedom, the equation can be written as this. So 2 minus pi plus n. Sorry, this is not pi, this is apa ni? Saya dah lupa. Yes, this is pi. Okay, this is pi. Okay, so pi is the number of phases and n, capital N, is the number of species. Okay, so in case of pure substance, okay, so when you have pure substance, the number of species would be 1. Okay, so you have the pure substance, N will be equals 1. Because you have only one species, only one type of substance. So the N will be 1. And then the number of phases will depend on the pressure and temperature. Okay, so for example, if you have this pressure here, okay, let's say you have the pressure somewhere here. Okay, so if let's say the temperature is between this point until this point, then it will be in solid phase. So you have one phase, one type of phase only. Okay, but if let's say the temperature is exactly on this point, kat sini kan, exactly at this point, the temperature. So it falls on the line, on the fusion curve. So in this case, you will have two phases, which is the solid and liquid. So in this case, pi equals 2. Okay. So depending on the pressure and the temperature, the number of phases will change. Okay. So in this case, if the pressure and the temperature is somewhere in the region, in the solid region or in the liquid region or the gas or the vapor region, meaning that it doesn't fall on the line, then you will have one phase only. Okay. But if the pressure and the temperature falls on the line, whether the fusion curve, the vaporization curve, or the sublimation curve, then it means you have two phases coexisting. So in this case, the pi becomes 2. Okay, another condition is when you have the P and T falls exactly on the triple point here, this point. Okay, this green point here. So in this case, you will have 3 phases. So in this case, pi equals 3. So you can calculate the degrees of freedom. Okay. Okay, for example, just now, if you have the triple point. So triple point, kalau triple point tadi, your F will be F equals 2 minus 3 because you have the 3 phases plus 1 because you have one species. So this is equal 0. Okay, right? So here, it's already written here. For the triple point, the degree of freedom is 0. Or in other words, it's called invariant, meaning that you cannot have any freedom. I mean, it's already fixed. So the triple point is already fixed. When you have that pressure and that temperature for the triple point, you cannot change it anymore. Okay. So it's specific for each species. For example, for methanol, you have the specific pressure and the specific temperature for that triple point. Okay. For water, you have another pressure, another temperature. Okay. For other substance, acetone, for example, you have another values for the pressure and the temperature, and it's already fixed. You cannot change it. That's why it's called invariant. So the degrees of freedom is 0. Okay. For the lines, okay, those points that fall exactly on the line, if you calculate, okay, so 2 minus 2 plus 1, right? So it equals 1. So in this case, the degrees of freedom is 1. In other words, it's also called univariant. Okay, meaning that in this case, if you fix one parameter properties, for example, if you fix the pressure, you can only have one temperature. Okay. What it means is that, okay, just now I show you this dashed line, okay, for P, yeah. So let's say you have this P value here. So if you, let's say you fix this P at this value, if you want to find the T on the fusion curve, you can only have this one value T here. Okay, there's only one T value. And then if you want to find the T value for the vaporization curve on this line that falls exactly here, so you can only find this T. Okay, so that what it means. Okay, you can only have 1 degree of freedom. Okay, so in contrast, for the single region, single phase region, okay, the degree of freedom will become, so if you calculate 2 minus 1 plus 1, okay, so the degrees of freedom F becomes 2 here, okay, here the degree of freedom F becomes 2. In other words, it's called divariant, meaning that you can apa tu? You can actually set any 2 parameters. Okay, so you can let's say you have the pressure here, P. Any temperature within this region will be you can have the one phase region. Okay. Okay, so in this case, for the divariant, for the F equals 2, you need to set the values of pressure and temperature by yourself. Okay, if you just set the pressure, you cannot automatically determine the temperature because you have so many temperature here. Okay, any temperature here can be the value that you want. So you need to determine both the pressure and the temperature in order for you to get the single phase region. Okay, so that is the meaning of the degree of freedom. So you can have 0 invariant on the triple point, and then you have the univariant 1 freedom on the line, and then divariant 2 degrees of freedom where you have the single phase region. Okay. All right. So just now is the PT diagram. You can also write the diagram in terms of PV. Yeah. So now you have the P, the pressure on the y-axis, and then the volume on the x-axis. Again, remember in this book, when we write V, it means the specific volume or the molar volume, meaning that volume per unit mole or volume per unit mass. Okay. So in this case, still you can see the different region, the different phases. Okay. It's just that just now in the PT diagram, for the phase boundaries meaning that this line, yeah, the fusion curve, the vaporization, or the sublimation curve. When you write when you draw the PV diagram, these phase boundaries, it will show you areas or region. Okay, so here you have this solid region and then the liquid region. So in between the solid and the liquid, you will have these areas, these small narrow areas here, which is the solid liquid region or area. Okay, and then in between the liquid region and the vapor region, you will have the liquid/vapor region. Okay, and then here you have the solid/vapor region. Okay, and then the triple point. Just now in the PT, you will just see 1 point, but on the PV diagram, you will see it becomes a line. Okay. All right. Still, you will have the critical point C. So now the critical point here is the top point here of the liquid vapor region. Okay. So this is the critical point. Again, you have the critical pressure PC and the critical temperature TC. Now the temperature here is shown by lines. Okay. In this case, the dashed line. Okay. So if you want to see other temperature, it becomes this dash line. Okay, so this dash line is showing you the different temperature. Okay, for example, the lowest line, dash line here is temperature T2. And then here is temperature T1. And T1 and T2, they are lower than the critical temperature. Okay. And then here you have the temperature T, which is higher than the critical temperature. So the line is above the critical temperature line. Okay. So these are lines, temperature lines here, T1, T2, Tc, we call it isotherms. Okay. This isotherm. So isotherms, iso means same. Okay. So which means that this is at the same temperature. Okay. Right. Okay, so there are some terms that I need to explain here. Okay, first you can see this apa tu dome-like shape yang ini this blue line and then the green line here. Okay. Okay, so this line is showing you the saturated line. Okay, for example, this blue line here is the single phase saturated liquid at boiling temperature. Okay, and then from point C to here D, this is the saturated vapor. Okay, so you have this saturated liquid line, the blue line, and then the saturated vapor line, the green line. Okay, and if you have so anywhere in between these two lines, for example, this point J or point K is where you have both phases. You have both liquid and vapor coexist in equilibrium. Okay. And then of course, if you are at point C, then that is the critical point. Okay. And above point C, you have the supercritical or the fluid region. Okay, so the way you read this diagram is that normally we will refer to the isotherm, to a specific temperature line. So if let's say you are referring to this T2 line, okay, so first here, you start with liquid, yeah? So you have the substance in liquid form. So when you decrease the pressure, it will slowly move here until it reaches this point, this line. So now here at this point, the substance is at saturated liquid. Okay, so saturated liquid, and then you have the pressure. The pressure is constant here, this line, but the temperature is increasing. So in between this point to this point, this is where the liquid and vapor coexist. Okay, once it reaches this point here on the saturated vapor line, it becomes saturated vapor. If you increase the temperature again, it will become vapor. Okay, 100% vapor. Okay, so you can trace the behavior of the substance according to the isotherm. Okay, we also have this term here, subcool liquid. So subcool liquid is liquid at the temperature lower than the boiling point temperature. So for example, water, the boiling point is 100 degrees Celsius, right? So if you have water at 80 degrees Celsius or water at room temperature, then you can refer to that water as subcool water. Okay. If we say superheated vapor, meaning that the vapor is at the temperature higher than boiling temperature. So again, if you take water, if let's say you have water vapor at 200 degrees Celsius, then we can say that the water is superheated. Okay. Because later in the book you will see this term, yes, subcool and subcool liquid and superheated vapor. So you need to remember these terms. All right. Okay, this is just what happens if you draw the diagram, the PVT diagram in 3 dimension. Okay, so you have the pressure, temperature, and also the specific or the molar volume. Okay, so you can see that on the PT, the lines on the PT diagram, it can become regions on the PV diagram. Okay. Okay, so as this is actually the summary of what I have explained to you using the PV and the PT diagram. Okay, so any fluid could be in one of below conditions. So when we say fluid, fluid means liquid or vapor or gas. Yeah, so any fluid can be in one of below conditions. So it can be in single phase liquid. So if it's within the liquid region, then you can say it's single phase liquid, or it can be in single phase gas, or it can be in two phases liquid and gas. So if you refer back to the PT diagram, when you have the lines, if it falls, let's go back to the here. Okay, so if it falls on this vaporization curve here, then you can say that the substance or the fluid exists in two phases, liquid and gas. Okay, so generally, if the system is at any T or P, okay, so if the T is higher than TC, critical temperature, then the substance is in gas phase. Okay, if the T is lower than TC and P is higher than PC, then it's in liquid phase. Okay, if it's the T is lower than TC, P is lower than PC, you need to refer to the boiling point. If the T is higher than boiling point, then it becomes gas. Okay, if same as above, but the temperature is lower than the boiling point, then it becomes liquid. Okay, if the temperature is at the boiling point, then it becomes two phase. Okay, so for H2O, for water, the critical temperature is 374 degrees Celsius and the PC is 220 bar. Okay. Okay, because we might ask you, okay, we give you a specific temperature or pressure. Okay, let's say I ask you, okay, water at 400 degrees Celsius. So what is the phase of this water? So here you can already see that the temperature is 400 degrees C. It's higher than the TC. So it means that the water must be in gas phase. Okay. So if you're given a temperature or a specific value of the pressure, you can actually determine whether the substance is in gas or in liquid. Okay. Now, the boiling point and the vapor pressure could be obtained from the Antoine equation. So later in the, I think chapter 11 or 12, you will learn more about this Antoine equation. So P sat is the vapor pressure or the saturated pressure. So this, if you see from the equation, the saturated pressure or the vapor pressure is a function of T. So T is the temperature. A, B, C is constant. Okay, it's a fixed parameter. So you can see that if you have the temperature, you can determine the vapor pressure from this equation. Okay. Example, this is the Antoine equation for H2O. So this is the value of A, this is value of B, and this is the value for C. So you just insert the given temperature, you can get P. Okay. All right. So liquid phase, V is almost stable and does not depend on P and T. What it means is that the volume is almost fixed. Okay. let's say you have 100 milliliter of water. Okay, so the volume is 100 milliliter. Even if you if you change the temperature or if you change the pressure, the volume normally does not change much if it's in liquid. Okay, if let's say you have 100 milliliter at room temperature and if you heat the liquid to say 70 degrees Celsius, so the volume normally is still the same, 100 milliliter. Okay, but for the gas phase, the V of pure substance depends on T and P. If you change the temperature, if you change the pressure, normally the volume will change a lot. Okay, so the mathematical equation or the mathematical relation between PVT of pure substance is called the equation of state. So the equation of state is connecting the P, V, and T. Okay, so you can see this term PVT in the equation. Why we call it equation of state is because the equation is showing you the state of the substance. It can be whether the substance is in liquid, in gas, or in solid state. So it depends on the pressure, the volume, and also the temperature. Okay. So from the regions of the diagram where a single phase exists, it implies a relation connecting P, V, and T. So we can express the equation of state like this, yeah. So F, the function, is they can be expressed in these three parameters, P, V, T, equals 0. This is how you write. Okay, when you have an equation and the equation is in a function of a specific parameters, we can write as this. Okay. And the simplest equation of state, so in short, we write EOS, equation of state. So the simplest EOS is actually the ideal gas law. So I think you have learned about ideal gas before this, probably in Master Form 5, I think. You learn about PV, ideal gas, okay? So this is the equation for ideal gas. Okay, and maybe before this, you learn the equations is something like this, PV equals nRT, right? So in this case, the N is the mole number and V is the total volume. But remember in this book, in this course, we use the symbol V is showing you the molar volume. So this V here is actually already per mole. That's why we do not write N anymore here, okay? So it's the same equation, it's just that we use the different symbol for the volume. So in this book, if you want to write the N, if you want to include the mole number, we will write like this, P VT. So VT is the total volume equals nRT. Okay. All right. So the ideal gas law can be used for low pressure. Okay. So when the pressure is low enough, the gas actually behaves like ideal gas. And we will discuss more about ideal gas later. Okay, so to solve the equation of state, you need to express the equation like this. So if you have V, then you have the function of V in terms of P and T. Okay, and then if you have P, then the function is in terms of V and T. If you have T and the function, then the function will be in terms of P and V. Okay, because you have the three parameters P, V, T. Okay. Okay, so we are now on, if you are referring to your textbook, we are on page 86. Sorry, 68, yeah. Okay, let's continue. Okay, just now I have explained to you that when you want to find the equation for V, you can express the function as in terms of P and T, yeah. So we can also write this as this, yeah. V equals V in the function of P and T. Okay, so if you have this equation here, you can actually do the partial derivative of the equation. It becomes like this. So this is purely mathematics, yeah. Yang daripada sini kepada sini, this is purely mathematics. I think you have learned this in your first year punya differential equation punya class, I think. Okay, so this is purely mathematics. When you have this equation, you can write write the equation in terms of this partial derivative, yeah. So you have dv, okay, and then you have dv over dt, p constant times dt plus dv over dp constant t times dp. Okay. Okay, so if we divide this equation with v, okay, so you can get this lower equation, yeah. So you divide with v, so you have dv over v, and then you have 1 over v here and 1 over v here, okay. And we can replace this term yang warna biru or light purple ni, we can actually replace with beta, and then this light pink here we can substitute with kappa, yeah. So beta is called the volume expansivity and the kappa is called the isothermal compressibility. Okay, just note that here the symbol here we have negative here. Okay, so when you have this symbol equation tapi dia ada 3 line, that means defined as. So the volume expansivity beta is defined as this equation. Okay, and the isothermal compressibility kappa is defined as this equation. Okay, hence you can rewrite this equation here in terms of beta and kappa. So you have beta dv over v equals beta times dt minus kappa times dp. So this is equation 3.4 on page 68. Okay. Right. So next, if you do integration to this equation, this you integrate, you can get equation 3.5. Okay, so you get ln v2 over v1 equals beta bracket t2 minus t1 minus kappa bracket p2 minus p1. Okay. Okay, so for liquid phase, remember just now I explained to you for liquid, the volume does not depend much on the pressure and the temperature. So if you have water at 20 degrees Celsius, 100 milliliter, if you increase the temperature to say 70 degrees Celsius, it will still remain 100 milliliter. So this is what we call incompressible fluid. Even if you compress, you increase the pressure, the liquid volume will still be the same. Okay, so for liquid, we always consider as incompressible fluid. So in this case, the beta and the kappa values, they are very small, close to 0. Okay. Alright, so dalam slide ni tak ada So you can refer to example 3.1, page 69 on the textbook. Here, you are given an example of liquid acetone. So the given value of beta and kappa, you can see that it's very small. Yeah. So for beta is 1.4487 times 10 to the power of negative 3. So it's almost 0. And then kappa is 62 times 10 to the power of negative 6. So you can see that the beta and kappa for liquid, they are very small, close to 0. Okay. All right. So up to this point, any questions? So let me just summarize again. So for this part, you need to understand this PV and also the PT diagram. Okay, you need to be able to identify the different region, the solid, liquid, and gas. So we are more interested in the liquid and the gas region. Why? Because later you will see in the later part of the book that most chemical reactions they involve these two phases, liquid and gas. Solid ni kita interested juga, cumanya solid ni even if you change the pressure or the temperature, normally dia tak berubah banyak. Okay, but for gas, if you change the temperature a bit, it will change the volume contohnya. So that's why we are more interested in the gas phase and also the liquid phase compared to solid. Okay, so you should be able to differentiate the three region, and then you should be able to understand what the lines mean. Okay, so the line means that the substance exists in two phases. Yeah, and then also you can identify the triple point and also the critical point. Okay, so same goes with the PV diagram. So also PV diagram, you can see the different the single phase region. But also you can find the two-phase region, yeah, and you can identify the critical point and also the triple point. Okay, and then if we give you a temperature and a pressure, you should be able to know whether that substance exists in gas, in liquid, or it's in two-phase, yeah. Okay, kalau tak ada soalan, we will move on to the next part, which is the virial equations of state. So remember just now I explained to you that the PVT we can express in terms of equation of state. So virial equation of state is one of the type of equation. Okay. All right. So first we look at the gas phase. So virial equations of state for the gas phase. Okay, isotherms for gases and vapors refer to figure 3.2b page 70 are relatively simple curves for which V decreases as P increases. So kat mana kita tengok balik tadi the isotherm. Here, yang ini. You have the PV diagram. So this isotherm, the lines where it shows the different temperature. So this line you can actually write in a simple mathematical equation, which is the virial equation, yeah? Okay. Okay, so they are relatively simple curves for which V decreases as P increases. Okay, you have the PV diagram. So you have the isotherm, something like this, kan? Okay, T. So this line is relatively simple. V decreases as P increases. Okay, so PV can be represented analytically as a function of P. So this line you can actually express as this equation. Okay, PV equals A plus BP plus CP squared plus ... Okay, and then if you replace B here with B is defined as A B dash and then C equals A C dash, etc., then you can also write the equation as this. PV equals A bracket 1 plus B dash P plus C dash P squared and so on. Okay, so this is equation 3.6 on page 70. Okay, page 70. So A, B dash, C dash, etc. They are the constants for a given T and chemical species. Okay. So parameters B dash, C dash, etc. in this equation, they are species dependent, meaning that it depends on the type of substance. Okay, kalau methanol, you have the specific value for B dash, C dash. Kalau water, you have the specific value for B dash, C dash. So they are species dependent, and they are functions of temperature, meaning it depends on the temperature. But parameter A is found to be the same T function for all chemical species. Okay, meaning that untuk parameter A ni dia it's not species dependent. For all chemical species, you can use the same equation, which is of T function. Depends on T only. Yeah. Okay, next is about universal gas constant. I'm sure you have heard about universal gas constant, which is the R. Can when you have the ideal gas equation, you have this R. So R is a constant. So R is called the universal gas constant. So macam mana kita dapatkan a value of this universal gas constant? It's actually based on this experimental data. Okay. Okay. So when you have several types of substance, yeah. So in this case, if you refer to this diagram is on page 70, yeah, page 3. Figure 3.4, page 70. If you plot the data, yeah. So here, y-axis is PV, and the x-axis is P. So if you plot the data of PV versus P for different species, you can actually see that the line is approaching the same point here. Okay, if you have dekat sini kita ada hydrogen, H2, nitrogen, air, and then oxygen. Even the species is different. If you plot the graph, you can see that it all approaches the same point here at pressure 0. Here. So we can put this point here as PV bracket subscript T with the star. Okay, and this value is actually the same, yeah, for any species. We can determine this value experimentally, and this is the value, yeah, 22,711.8 centimeter cubic bar per mole. Okay, so this is the value that we assign as here. Just now, remember A is a function of T, and it applies for all species. Yeah, so this is a function of T, and we can define this as RT. Okay, so if we assign the value of 273.16 Kelvin to the temperature of the triple point of water. Okay, so this is the triple point of water. You can get the value of R. Okay. Okay, so you have yang tadi ni kita dapat experimentally 22,000 something ni. We divide with the triple point of water, so you can get the value of R here. Okay, so R is the universal gas constant. Its value is determined from experimental PVT data. Okay, so this is the value of R, 83.1447 centimeter cubic bar per mole per Kelvin. Okay, so this is how researchers ataupun they determine the value of R. Okay. So for the value of R, if you notice, these units, they are not the SI unit. So kalau if you want to convert to the SI unit, you can do the unit conversion, or you can refer to appendix A. Yeah? So if you have this textbook, you can refer to appendix A, and it will give you the values of R for other units. Here. So this is appendix. I'm not sure if you can see. This is appendix A. On the bottom here, you have the values of the universal gas constant. So it gives you the values of R in many different units. Okay. So I think probably you are more familiar with the SI unit, which is 8.314 joule per mole per Kelvin. Okay. All right. So now going back to the virial equations for gas phase, we can start the equation using this equation here, equation 3.10. Macam mana kita dapat? So remember you have the equation for ideal gas, which is PV equals RT. So in this case, we just add a parameter Z here. Z ataupun Z kat sini ya. So you can write Z like this. Okay. And Z here is called the compressibility factor. So this is by definition, yeah. So by definition, compressibility factor is defined as PV over RT. Okay, and then from the previous equation, yang tadi you have the virial equation, this one here, PV equals something something. You can substitute into 3.10 to get equation 3.11. Okay, so you can express Z. Okay, Z equals 1 plus B dash P plus C dash P squared plus D dash P cubic plus dot dot dot. So this form of equation where you have kat sini you ada, actually you have P power 0 kan. Sini ada P kuasa kosong, and then the next term you have P kuasa 1, P kuasa 2, P kuasa 3. This form of equation is what we call the virial equation or the virial expansion. Okay, so alternatively, we can also write in terms of volume. So again, you have this V kuasa 1, V kuasa 2, V kuasa 3. So this is also another form of virial equation. Okay, so you can either write Z in term of pressure P or in term of molar volume V. Okay, so B dash, C dash, D dash, B, C, D, etc. They are called the virial coefficients. Okay, the B dash and B is called the second virial coefficient sebab dia is they are on the second term. So yang ini first term, second term, third term, fourth term, and so on. Okay, so they are called the second virial coefficients, whereas the C dash and C is called the third virial coefficient. Okay, and these virial coefficients, they only depend on T. They are a function of T only, temperature only. And you can obtain the coefficients from PVT data. Okay, for example, untuk B dash, the equation is here. Okay, B dash equals B over RT. Okay, and you can also have the equation for C dash and also D dash. So you can see it's a function of T only. You don't find P inside the equation. Okay, right. Okay. Okay, so virial expansion arise on account of molecular interaction. Term B over V arises on account of interactions between pairs of molecules, and the C over V squared term on account of three body interactions. So, okay, if you look at this virial equation here, Z, so this is, one is the first term. So the second term is based on the interaction between pairs of molecules, and then the third term is based on three body interaction. Okay, So for ideal gas, the interaction, the molecular interaction is assumed to be not exist. Okay, so kita boleh assume second term, third term, and subsequently the fourth and so on, all these terms become zero. Okay, so in this case, the Z, okay, the compressibility factor will become 1, okay, for ideal gas. So therefore, the equation of state for ideal gas becomes this: PV equals RT, because Z is 1. Okay. So macam mana? What are the conditions or what are the situations that you can assume a specific gas behave like an ideal gas? So here, okay, as P approaching 0, V becomes infinity, and then Z approaches unity. Okay, so in this case, you can any gas, if the pressure is low enough, is near to 0, then you can assume that the gas is behaving like an ideal gas. Okay, so for ideal gas, you can conveniently use this equation PV equals RT. Okay, so the ideal gas, what are the considerations ataupun apa yang kita assume dalam ideal gas? Okay, number one, no molecular interactions. And then the volume of molecules is much smaller or negligible compared to the total volume occupied by the gas. Okay, so these two assumptions, they are valid at P approaching 0. Okay. I think we can stop here. Yeah, I think we better stop here because the next part is going to take some time to explain. Okay. So do you have any questions so far? So we have learned about the PVT diagram, how to determine whether the substance is in solid, liquid ataupun gas based on the PVT diagram. And also you have learned about the ideal gas equation and also about the universal gas constant R. Okay, and a bit on the virial expansion or the virial equation of state. Any questions? Okay, so all right. So for the slides, I have not updated the slide. I have not uploaded the slide on e-learning. I will do later. Yeah, sebab normally I use the slides first for teaching, and then I will upload the latest version because sometimes I put some notes, additional notes on the slide, so you can understand better. Oh, another thing is about the textbook kan. Last time I told you that you have the current version or the latest edition is the 8th edition. And if you want to buy the textbook, that's probably the only edition that is available in the market. But I advise you to use the 7th edition because of the flow and so on. So we decided that we will allow you to use the photocopy version of the 7th edition book. Okay, meaning that you can, if let's say we have face-to-face final exam, you can bring the photocopy version of this book to the examination hall. Okay. Sebab your final exam, as well as the test 1 and test 2 will be open book. Okay, you can use the textbook. Okay. Ada soalan?
So far, no, Doctor.
Okay. So if no questions, so I will stop here. I will see you all on Thursday. Okay? Boleh?
Boleh,
Okay.
Doctor.
Boleh, thank you, Doctor. Have
Okay,
a
so
nice
thank you everyone. I will see you again. Take care.
Thank you, Doctor.